Okay, so this is quantum computing and RPGs for the Gencon Online. Today we'll be talking a little bit about what quantum computation is and what you can and cannot do with it, how you actually build a quantum computer, and then we're going to start. I'm going to show you what could possibly be the worst RPG system ever. I mean, a role-playing system with great educational value. And hopefully some of you are either writers or game designers or something like that. So hopefully this should give you a basis of what's possible and what is the current state of science right now. And then you can add the fiction part of the science fiction. Okay, cool. So what I'm going to do for most of this talk is compare quantum phenomena to probability. This is Gencon, and at Gencon you play lots of games of chance. So by now hopefully you have developed an intuition of what a good result is or what to expect with games of probability and things with probability. So we're going to build on this. We're going to build on this intuition and kind of use that to explain some quantum computation and quantum phenomenon. So like of chance, if you roll, there's multiple possible outcomes, and you don't get the same outcome every time. So if you roll a dice over and over again, you get a different result every time. However, you can have results that are correlated or more likely than others. So if you roll like a 3d6, it's much more likely that you roll like a 10 or 11 rather than an 18 or a 3. So if you've played, any games where you roll that kind of dice, you'll know that you usually get something in the middle rather than something at the sides. So, so these are things that are true for quantum as well. But some things that are different than quantum are that probabilities are always positive. However, in quantum amplitudes, which are a little different than probability, but you use amplitudes to calculate a probability, they can be negative and can be subtracted. So because of this, this is very different. So you can have things like destructive interference where things cancel out, which is not necessarily true in probability. And you can also have something called entanglement, where things can be correlated in ways that are very difficult to happen if you just have like a normal probability. So we're going to use a game of chance as an analogy for quantum, but it is an analogy, so it's not perfect. And sooner or later, our intuition about probability is going to start to break down. So when this happens, I might interest you in a quantum game. So we'll talk about that too. Okay, so let's talk about a game called poker. In poker, you draw 5 random cards. And before you look at the cards could be anything. You could have many different possibilities. Could be a pair, straight flush, full house, all sorts of different possibilities. And all these hands have different probabilities. It's more likely you'll get a pair than a straight flush. But eventually in this game, you turn your cards over and show your cards. And this is kind of like measuring the cards. Now you know what the hand is, either your own hand or your opponent's hand. So if we compare this to quantum computation, we do a lot of the same sort of things. And some of them are similar and some of them are a little bit different. So instead of drawing 5 random cards, what we're going to do is kind of draw 5 random quantum states and put them into a superposition. So this is kind of a random state where we don't necessarily know what the card or the quantum state is. And then at the end of our quantum computation, we're going to flip the cards over and we're going to measure our state. And once that happens, we know what it is. So this is kind of similar to poker in that, when you start out, you don't know what the cards are, and they could be anything, and there's many different cards. But at the end, once you flip over the cards, you know what they are. So the difference between quantum and probability here is that in the state where you have a poker hand, you know it's either a pair or a straight or something else. There's only one possibility that they're holding. You might not necessarily know what it is, but there's only one possibility out of many. In a quantum superposition, this or is changed to an and. So you might have a pair and a straight and a high card and a flush and all these different possibilities which kind of exist at the same time. So maybe we have to like adjust our analogy here and say, this analogy is more like the cards while they're being shuffled. So while you're shuffling them, there's not necessarily like a poker hand. It's kind of all the different kinds. Or if you think about rolling a dice or flipping a coin, while the coin is in the air or while the dice is in the air, talking about what the result is doesn't matter because the result hasn't been determined, right? So while a coin is flipping, it's heads and tails. It kind of is oscillating there. And then the same thing with a dice. If you roll a dice, while it's in the air, it's kind of spinning. So it's in multiple states. So saying like, what is the possibility doesn't really make sense in that state. It's the same way with quantum superposition, in which before you measure it, it's all of these possibilities at the same time. Okay, cool. So, and because of that, if we modify the quantum state during this weird time where it's in this superposition and there's many different combinations at the same time, we can do a lot of things at the same time. So if you're like in the middle of a poker game or something and you have to do something, so in draw poker, you exchange 2 of your cards for 2 other cards. So in that instance, you are changing your one specific hand. So you know what poker hand you have, and you're modifying it in a specific way. The thing with quantum superposition is that since this is all the possibilities and at the same time, you're changing all of those hands simultaneously. And it's not until we measure that we know what the result was. And in particular, one thing that's not true about poker hands or other, random probabilities is that quantum have a sign. So the amplitude has a sign, so things can be added and subtracted. So you can get things like constructive interference where probabilities become more likely, or destructive interference where things become less likely. Okay, so let's examine that a little bit more. So let's say we have a state where the cards are either all red or all black. So we know that, this hand that you're holding is either 5 red cards or 5 black cards. So this is a little bit harder to do in a poker hand. It's very difficult to kind of get this state where you have all 5 red cards or all 5 black cards. You can't really do that by just taking like one card at a time. So if you took 5 red cards and 5 black cards and shuffled them together and then drew 5, you wouldn't get this probability distribution. You get, some of the time you get like 3 red cards and 2 black cards. So in order to kind of like get this probability where you have only 5 red cards or only 5 black cards, you would have to kind of do some sort of magic trick or stack the deck or something where, you keep all 5 cards behind your back and then you choose, all 5 cards at the same time. So with you can do this a lot easier, and this is called entanglement, where the states are correlated, the cards are correlated together. And right, so because of this, this allows us to do a lot of different things. So when we switch out of this poker analogy into something a little bit more quantum, we call them qubits. And qubits are not red or black. They're usually denoted 0 or 1. So we could have something where we have 2 qubits, and we guarantee that they're either both zeros or both ones, So this is called a Bell pair. It's also called an EPR pair, and EPR stands for Einstein, Podolsky, and Rosen. Einstein, you've probably heard of, a very famous physicist, came up with relativity among other things. Podolsky wasn't too famous outside of this term, but Rosen you might have heard of, because whenever a science fiction wants to be fancy, they call something an Einstein-Rosen bridge, and that's like a wormhole that you could, emerge in a different part of space. So these are, famous physicians of the early 20th century. And they thought this was pretty weird, and they kind of used this state to enunciate lots of this strangeness around quantumness. And they called it spooky action at a distance. So because of pairs like this, you can do things like teleportation. Now, this sounds like science fiction, so let's dive into this a little bit more. So let's say you have this state. We'll go back to our poker analogy for a little bit. So we have this hands, and we know that the hands are either all red or all black. So this is interesting, but what if we separate the hands? So we put, 3 cards in over here and 2 cards over here. And then we separate them by a great distance, either on the other side of the country or on the other side of like the solar system or galaxy. We separate them by a long way. So now this magic trick where we kept, 5 cards behind our back and we can switch them red or black. Now this is a lot harder to do because now, one half of the poker hand has no idea what the other half of the poker hand does. So you can't it's a lot harder to guarantee, if I flip mine over and I see red, what's going to happen way over on the other side of the country, right? So this was something Einstein, Podolsky, and Rosen looked at, and they said, what's even weirder is if we take another hand after we put them up and we do the same thing. So we make this correlated pair, this Bell pair again, and entangle it with our half of the poker hand, or our half of the Bell pair. So when we do this, now we know our new thing that that the other half has never seen before is kind of entangled with this half of the pair, which is also entangled with the other half of the pair that's way over on the other side of the country. So kind of by this weird transitive property, we know that all 3 of them are correlated or entangled. So what happens then? So now let's say that the first person who has the new one comes in, and so they first entangle it. So now we have sort of 3 triplet instead of a pair, where we have the red cards entangled with the black cards entangled with this new thing. So now the first person, if they actually measure this and figure out, did I have a red card or a black card, or did I have 0s and 1s, or what happened here? So if they measure this, and then they go and tell the second person what they measured, actually the person on the totally other end of the country will now have a state that's exactly the same as the new card. So even though that this card sort of never came into contact with that half of the pair that was on the other side of the country, we still kind of somehow managed to transport or teleport that information all the way across to them, which is kind of interesting and kind of weird, and what they meant by spooky action at a distance. Okay, so this slide's kind of a mess with all these crazy poker hands, so I'll go and show you what the actual circuit is. So I'm not going to go and explain all these different gates, but I'll just kind of show that this is, the technical circuit diagram for a teleportation circuit. And what it means is on this left side here is how you create this entangled Bell pair, and then you separate them, and you come in with this new qubit. So that's usually represented by the Greek letter psi, so it looks kind of cool. And then you entangle it with 1/2, then you measure it, and then you send the 2 bits over. And now this other person who never saw the new qubit psi now has the ability to reconstruct psi. So that's pretty interesting. It's kind of this weird teleportation. So that's pretty cool. Once we get quantum computers, we're going to have teleportation, just like Star Trek, right? So unfortunately, I would love to tell you we'd have Star Trek transporters over here, but we not. So one limitation here is this is only information. There's no actual matter being or like atoms or anything teleporting. It's just information. So if we kind of go back here, you know, we started with 3 qubits, 2 qubits on the top and 1 qubit at the bottom. And at the end, that's what we wind up with too. So we haven't actually like moved anything beyond information. So unfortunately, we're not going to get a Star Trek teleporter, but we could get faster than light communication, right? So that's pretty cool, and that's science fiction. But there's also another catch here. So if you were paying close attention here, in order to kind of reconstruct this state over here, this top person, usually denoted Alice and Bob. So Alice has to send her 2 bits over to Bob. So she has to tell Bob what she measured, whether it was 0 or 1. And doing that, sending those 2 bits has to be like classical communication. So you have to send it, you know, via the internet or via laser or something like that. And that's going to be contained by the speed of light. So unfortunately, you can't get faster than light communication either, even though that would be pretty cool. Okay, so if we can't do, yeah, so we have a question. Leaf?
Yeah, just real quick on that. Does the information psi available to anyone who's observing Alice send the first 2 bits to Bob, or is psi like only available to Bob?
Psi is only available to Bob. So you cannot get that information unless you're Bob. So Bob has it because it was entangled. It was part of the entangled pair, which was entangled with the original psi. So anyone else who's like eavesdropping only gets those 2 bits. They don't have enough to reconstruct psi.
Wow, that's actually pretty cool.
Yeah, I mean, it's still cool. It's not Star Trek teleportation. It is still very interesting. And it was something that, you know, puzzled Einstein, Podolsky, and Rosen, and sort of was not necessarily an argument against quantum mechanics, but one thing where they pointed out that this is really strange and non-local. Okay. Back to the presentation. So if we can't get teleportation, what can we do with quantum computation? So if we look at a classical computer, like our poker hands, can be in one state. And there's many states that it can be in, but it is always in one particular state. So often they call this like a finite state machine. So for instance, if we talk about like an 8-bit processor, so this was something like the old school NES, this 1 byte or 8 bits can be in one of 256 states. So this is why you had like 256 colors back in those days. However, if you're talking about qubits can be in any combination of those states. So it could be in a combination of state 1 and 2, or in a state combination of state 1 and 254, or a combination of 3, 7, 9, and 27 or something. You know, it could be in any of these like combinations. So that's actually 2 to the 2 to the 8th, which is 2 to the 2 to the 256, which is this gigantic number down here, which I don't know like even what the name of this would even be, but it's a very large number. So if we can kind of take advantage of that somehow, this is a huge amount of computation with just 8 qubits, right? So this was not my PhD advisor, but yeah, I'm going to post a video online. It might take me a little while to get it upload it and stuff, but I will post it. And this was a professor at the university I went to who said, this Hilbert space is a big place, and this is why, is because there are just so many possible states. And this is also assuming that all the states are of equal probability of happening. If you say like, well, state 7 is twice as much as state 37, then that even makes this number even larger. So there's a huge amount of information that is happening here if we can take advantage of it. And to kind of give this analogy, suppose we have 32 qubits. So 2 to the 32 is about 4 billion. So that's, give or take a factor of 2 about the size, about, the population of the Earth. So this is kind of like giving everyone in the Earth a lottery ticket that has your 32-bit number, that's your lottery number, and it has this amplitude, this probability that you're the winning state. And so every time we do an operation, so let's say we want to flip the last bit, everybody on the planet has to get together and switch the probability, switch their lottery ticket with the other person who's the same in the other 31 bits and, differing only in the bit we're flipping. So you have to go find that person who has the same lottery ticket except for 1 bit and switch numbers with them. And everybody on the planet is doing this at the same time. And that is just one operation of a quantum computer. So every time you do this operation, everybody on the planet is, doing stuff with their lottery tickets and switching them around. So this is a huge amount of computation that's happening at the same time. And every time you add a qubit, you multiply it by 2. So if you added 3 qubits, it would be like you had an Earth-sized population on every planet in the solar system. And this is a picture of a Bristol cone chip. It has 72 qubits. And this would be like if you had an Earth-sized population on every star in the Milky Way galaxy, and they were all switching lottery tickets. So this kind of computation grows exponentially large and, has a lot of potential to do something, right? So there is a piece of bad news, though, is that at the end of the day, you have to actually measure the qubits. So this is like saying, okay, out of all of these lottery tickets, I'm going to go ahead and pick one. I'm going to pick one probably that has a higher amplitude, but I'm going to pick one of them, and that lottery ticket that won, and everybody else disappears. So all of this kind of crazy computation suddenly disappears, and you just get one state, and it's like that state was the state that was there the whole time. So so this is kind of tricky, and like going back to our poker card analogy, this is like you called and then everybody flipped over your cards, and now all the probabilities are gone. You just know who won the hand, right? Or in this lottery analogy, we picked a lottery number and all the other ones got thrown in the trash. So let's talk about encryption. This is a common thing that people talk about in conjunction with quantum computers. So I'm going to vastly simplify the thing of like how encryption works to kind of give you an idea of like what the power and limitation of quantum computing is. So let's say that you have a quantum algorithm and it can generate a state that's all the possible cryptographic keys or all the possible passwords in the world, right? So the good news or bad news, depending on how you're looking at it, is one of these possibilities is a secret key. They somehow, your password or whatever is in this superposition. So one of them is the possibility. The flip side is the fact, the chance that you're just going to randomly pick this one is vanishingly small. So if we just kind of like did this and picked all the possible passwords with a quantum computer and then measured it right away, we'd get some random password like 652 blah, 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 blah is not your password. It's not the secret key. You lose. And then we'd have to, run this over and over again, and it would be no better than just trying to randomly guess passwords. So it looks like we can't really break encryption this way, and we can't like do it. So, but there's sort of this other corollary is that passwords and cryptographic keys are not just like random numbers. There's actually the system where, you know, the RSA, for instance, which is a common cryptographic protocol, is based on factoring and multiplying and factoring. So it's based on the fact that multiplying is easy, but factoring is very hard. So this is actually like a very structured problem, factoring a number. And in certain kind of areas, you could say it's like periodic in certain functions. So because it's periodic and it repeats, you can ask the of asking the quantum computer, what is the secret key? You can ask it, what is the period of this function? And now this is something where the probabilities kind of constructively interfere, and you're much more likely to get the answer because this is like a question that is true for many of the possibilities. So if the problem is periodic or structured, then you can kind of, if you're very careful about like what you're measuring, you can measure this in a way where you get something out that's better than just kind of randomly guessing. So obviously there's a lot of details there, but hopefully it kind of gives you a little bit of an idea of what's going on there. Okay, so hopefully I've given you a little bit of motivation that you might want a quantum computer lying around somewhere. So how do you actually make one? So there's a few different ways people have tried. You could use spin. So electrons and other particles have this thing called spin, and it was figured out in like 1920 that if you shoot these electrons through a magnetic field, some go up and some go down, and this is a quantum state. So, you know, this has been known for 100 years. Hopefully we could do something with it. But unfortunately, it's really hard to get this entanglement going on. Even though they're quantum states, it's hard to get entangled quantum states. So it's a little harder. You could use neutral atoms. Neutral atoms are quantum objects, and you can kind of use these by embedding impurities in crystals so they stay in one spot, and then shine lasers at them. This sort of works, but they're hard to manipulate and also hard to entangle together because they're neutral. They don't interact. Well, you could say, okay, well, neutral atoms are hard to work with. How about charged atoms? How about ions? And ion traps is actually probably one of the top ways to make a quantum computer right now. So you take a charged atom and you make electric fields where they all sort of pop into little squares called traps. So they kind of look like an egg carton. And you put one ion in each spot for every egg. So you can control these, but they have to be precise. It's hard to get exactly one ion in each bucket. But if you do, you can kind of move the buckets around and kind of get them to interact. So this is hard. People have done it. Honeywell, which makes like thermostats, you might have a Honeywell thermostat in your house. They also had, I think they spun it out into a new company, but they were working on ion traps. There's something called IonQ. It's a public company. They do ion traps. So it's promising. It might work. It's probably not the leading technology right now. Another one is lasers, photonics. So you could use photons. Photons are quantum objects. The good thing is they're very established technology. I mean, you might even have a laser pointer at home, right? You probably want a better one if you wanted to make a quantum computer, but same sort of idea. The bad news is photons move at the speed of light. So if you want to do quantum computation on them, you have to either have a really big quantum computer or do things very, very fast, right? Because they're, you know, gone before you try to do anything. However, this is good for a few applications like communication and networking and things like that, where you want the information to move. So if you want to communicate with someone, you want these photons zooming towards them. So for these sort of applications, photonics is really good. And in particular, China is very advanced in this area. So the thing about all of these is they're very small. They're, you're talking about something on the size of an atom, and that's really hard to work with. So the thing I'm going to talk to you a little bit about, which I work on, is called superconducting circuits. So superconducting circuits kind of work like this. So you can kind of imagine it sort of rubber band. So if you take a rubber band and you tie it down on both sides and then make it vibrate, these have certain stable states that are very discrete. So you can have, one thing going up and down, like the thing in the upper left here that goes boing, yoing, yoing, yoing. Or you could have something that has like two bumps where one's going up and one's going down, and that's like the first excited state. And then, 3, 4, 5 other things. So this is like a harmonic oscillator. So we're going to use a concept like that, except we're going to tie both the rubber bands together. And one thing to note with rubber bands, if you tried to do this and you tried to set up one of these crazy states, is the energy would quickly dissipate and you'd get something that looks like the upper left, where it's just one hump going up and down. And that's because of friction. Friction saps all your energy away. So you want something, in order to kind of keep these like higher states stable, you need something without friction. So when we do this, we're going to actually use an electric circuit rather than a rubber band. And the equivalent term of friction in electric circuits is resistance. So we want something with zero resistance, and this is called the superconductor. The bad thing about superconductors is, contrary to like a story that came out, some questionable science lately, you generally need very, 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 very cold conditions for something to be a superconductor. It doesn't really work well unless you cool it under like 3 Kelvin, which is very cold, about as cold as deep space. Okay, so this is kind of a schematic of a qubit. So this plus sign in the middle is kind of like our looped rubber band. The electric circuit kind of goes around this cross here. The thing on the top is how you measure it. So you connect something to the outside where you want to measure whether it's a 0 or 1 eventually. And then you have a drive line where you actually control the qubit. So this is kind of like pinging the rubber band in order to kind of do gates and change the state of this rubber band. You also have another line that connects it to other qubits. So you want to connect these so you have a whole bunch of them so you can get these cool entanglement features and actually make use of the quantum weirdness that we were talking about. So you put these kind of crosses in a grid like this. So each of these crosses is like a qubit, and each of the little like rectangles is a coupler that joins the 2 qubits. So you kind of allow the 2 rubber bands to connect and become one big rubber band for a little while in order to entangle them. And then you turn it off and make them 2 separate rubber bands when you don't want them entangled. So you kind of set it up in this complicated grid here. And then you print this grid on a chip. So this is an old chip, and you can see the scale here is about 1 centimeter. So this is about the size of a postage stamp. So these qubits, and you can see the qubits in the middle here are these little plus signs here. So they are kind of small in relative to like, us, but I mean, you can visually like see them. So these are much bigger than dealing with individual atoms, which is very nice. That, there's something that's a little bit easier to manipulate here. Okay. So you take these, this is actually like 2 sides of the chip. It's called a flip chip, and you flip them together to make this bonded device here. So this is the thing flipped together, and then you kind of mount it on this device. So this is after it's been flipped together. And then you put it in this thing called a package, which is like it has shielding and connections where you can connect things to the outside world. And put this thing in this bottom of this gigantic like golden chandelier looking thing. So this is called a dilution refrigerator. You might have seen pictures of this. So this is a way of how you kind of keep the qubits cool. So what you put the qubits at the very bottom, this chip kind of goes at the bottom, and each of these like platters is like a little bit warmer. So it starts at room temperature. The very top is room temperature, which is about 300 Kelvin. And then as you start to go down, you get to like 40 Kelvin and then 3 Kelvin and then, you know, below 1 Kelvin. And then that's where the qubit sits. And just to kind of note, deep space is like 2 to 3 Kelvin. So this is colder than deep space. So we have to keep it very, very cold. Okay. Right. So all these wires, so each qubit has one or more wires, usually about 3 wires connected to it for measurement and to control the qubits. So these input signals originate from the top, and they go down these wires, and as they're going down, they're coming from room temperature all the way down to absolute zero practically. So you need all sorts of filters to kind of like cool the signal down. And then on the way up, so then it hits the qubit, and the qubit does its thing, and then eventually you measure it, and the signal has to come back up. So then you have to amplify it and amplify it and amplify it till you can read it out at room temperature. And then meanwhile, there's all this liquid nitrogen or liquid helium that's kind of coming through pipes in the middle here. It's a little harder to see. And they cool all of these plates down to the temperatures that you want so that they stay really cool. And of course, you have to cover this whole thing up so that it's completely shielded from both light and any air particles that would be bouncing into it. So you kind of create a vacuum and put this big thing that's like a garbage can on top of it. Okay. Let's see here. So this is a picture of this thing, of the dilution refrigerator. So this top part is kind of like what it looks like when it's completely sealed. So there'd be another part that goes on the bottom here. And this is the dilution refrigerator with all the plates at the different temperatures. And then all of these kind of wires come in and out the top. And kind of this is, we've actually gotten better since this picture was taken, but this was, you know, early days where, you know, our wires were a little bit messier. And then they are connected to electronics, which kind of convert the signals from a classical computer from digital to analog. And then when they're coming back, analog back to digital. So that sort of in a nutshell is how quantum computing works. So let's get to, you know, role playing. What does role playing have to do with quantum? So I noticed there's a trend lately to have, you know, one-page simple RPGs like Honey Heist, where, you know, you need like 1 die and 1 page of rules. So I did decide to be contrarian and do the exact opposite, where you need, you know, a graduate level education and you need a supercomputer or a functioning quantum computer to actually run it, which could be the most ridiculous system ever. But okay, so all joking aside, I thought, you know, this would be an interesting way to help people learn a little bit about quantum computation. So by playing quantum games such as this game, or, you know, some of our other games like quantum chess and things like that, you might develop a little bit of intuition about how superposition and entanglement works, and start to understand some of these quantum processes intuitively, just like we do with games of chance, where, you know, like this armor class is going to be hard to hit or something, that you'll start to hopefully develop that intuition as you play these quantum games, and you'll hopefully have fun doing it. Okay, so how does it work? So our rules are like this. So we're going to have a character sheet or a character sheet. One sort of industry tip is, if you want to be a cool quantum professional, you have to take a perfectly reasonable word and put Q at the beginning or somewhere in the middle of it, so that it's quantum. So that's just a tip to make you look cool when you're trying to, do a quantum lecture. So we're going to have a quantum character who has qubits as hit points, or QPs. And for each level that you have, you'll have 1 hit point. So you gain 1 hit point, and each hit point is going to be a qubit. Okay, so as you kind of progress and gain experience, either through, winning a battle, or, if you're like have a DM or something like that, then they can award you experience in the form of quantum gates. So your quantum gates get added to your character sheet. And as soon as you have as many gates as you do levels on each single hit point, then you gain a new hit point. You go up a level. So if you have, in order to get to level 3, you need 2 gates on 2 hit points. And then to get to level 4, you need 3 gates on all 3 hit points, and so on. So it sort of gets a little harder to level as you go up. Okay, and each of these gates affect the state of your qubit. So you kind of start in a different state. Okay, so how you do battles is you take everybody's character sheet and put them together in one gigantic quantum circuit. So, you could have a party of, players who each have a certain number of hit points, and then versus enemies that all have different character sheets. And the goal here is to measure the enemies, and you want to measure them as zeros and measure yourself as ones. So if you measure them as 0, they are downed or defeated. And if you measure them as 1, they manage to escape and you don't get any XP. So you want to measure them as zeros. So in order to kind of do that, you have to understand, well, what are all of these, gates doing to the qubit? Can I measure them right now and get a 0, or am I going to measure them and get a 1, or some combination? And every round, you're going to get a chance to do an action. So different character classes have different actions. So an analyst can measure or sample qubits. Engineers can apply different gates to the qubit. So if you know what their circuit is, you can apply the proper gates to get them into a 0 state, and then use your analyst to measure them. Okay, so, and hopefully by kind of doing this and seeing these enemies, you'll kind of get a feel for how quantum circuits work, because you'll have to sort of undo them and get them back to 0 and then measure them. Okay, so I'll just go through kind of one example, and this is called the cat state. It's very simple, similar to like the bell state we were talking about, or the poker hand that's all red and all black. So this is a 5-qubit state. You can tell that it has 5 lines here. And this first gate here is called the Hadamard gate. It takes a 0 state so it starts the qubit starts in 0. And this gate takes a 0 and it puts it into an equal superposition. So it's both 0 and 1 at the same time. These other gates are called controlled NOT gates, and they're on every single other qubit. And this gate, what this does is if the top qubit is 0, it does nothing. If the top qubit is 1, then it's going to flip that other bit. So this first qubit puts it in a superposition of 0 and 1. So if it's in the 0 state, all these controlled knots do nothing. And if it's in the 1 state, all the controlled knots flip all the qubits. So we wind up actually only getting 2 different states. One is all zeros. If the first qubit is 0, all of them will be 0. And if the top qubit's 1, they'll all be 1 because they all get flipped. So we get this equal superposition of all zeros and all ones. So this is kind of an interesting state in that, if you measure one of the qubits, any particular one, it looks random. It looks like it's only going to be, 50-50 of zeros and ones. But there's a little bit more to this state, because if you measure 1, you already know that all the rest of the qubits are going to be the same state. So if you want to like defeat an enemy, or like a Schrodinger's cat kind of enemy that has this state, there's sort of this strategy you could use. Well, I mean, I'm sure there's multiple strategies, but one strategy is could be that you measure one of the qubits, and then you see, okay, it's either a 0 or a 1. And now if it's 0, then I can just go and measure all the rest because I know there's 0. And if it's a 1, then I know that I have to flip all the other qubits to make them zeros and measure them in order to kind of win the battle. So hopefully, like if we get some states like this and some enemies like this, where you have the sort of like a mini puzzle here, you can start to understand some of the stuff on quantum states and how they work. Okay, so with that in mind, I created like a small text adventure game that you can go and try out. You can go to tinyurl.com/quantum-rpg, and it should go to this thing. The whole thing is open source, so you can try it out, modify it, download it, change it, break it. I know when I was young, I loved, messing around with games and making them say stupid stuff. So you're more than welcome to try that here. And then, it's also if you want to extend the game. So for instance, I don't have skill checks or something. And if you come up with a cool quantum way to do skill checks, you could, add it in here. That would be awesome, or suggest it as a feature. If you want to learn more about quantum stuff, you can also go to quantumai.google. There's a whole education page on there. You can do a virtual tour of our lab. You could do, there's all sorts of stuff about different algorithms that we run and different, there's a few games on there too. It's kind of interesting. So that's another thing you can do. I guess I will quickly